If you wanted a review of freshman chemistry and first semester organic, I hope you listened to part one of this video where I defined pH and I talked a little bit about how to work with logarithms and exponents, and I described the underlying idea of how buffers work. Now I want to go into this a little bit more rigorously and mathematically, and we're going to look at the Henderson-Hasselbalch equation. Henderson-Hasselbalch is based upon some broad-reaching chemical principles that may be even more important than Henderson-Hasselbalch itself. One of those principles is called the equilibrium constant of a chemical reaction. Let's say that you have an enzyme that takes A and B and converts it to C and D. No reaction goes to completion, meaning if you start with a whole bunch of AB over a period of time till it reaches equilibrium, there will be some AB and some CD. If you start with pure CD, it will form some A and B. But whether you started with only AB or only CD or only a mixture of both, regardless, at the end of the day, when equilibrium is reached, you will have the same amount of products over reactants, regardless of the starting conditions. And that's because it depends upon the relative chemical energy of products over reactants. And so in this reaction, that would be C times D over A times B. Will you write a chemical equilibrium constant for an acid dissociation reaction? That's where an acid dissociates into a proton and its conjugate base. Please go ahead and write that based upon what we just said. Now I'm going to move on. As an example, let's look at acetic acid. The products will be the acetate conjugate base and a proton, and the reactants will simply be acetic acid, the conjugate acid. So the Ka, the dissociation constant, will be the concentration of protons times the concentration of the conjugate base over the concentration of the conjugate acid. Now, will you define the pKa of an acid? Please do so, and you do know what it is. I'll give you a clue. What is pH? It's the same thing. Okay, let's look at that. So, of course, the pH is the negative log of the H, just as the pKa is the negative log of the Ka. And by using this same logarithmic function on both pH and pKa, it can somewhat simplify our working with them mathematically. Now, it also happens that the pKa of an acid is the same as the pH at which an acid is half protonated and half deprotonated. So in other words, if we took acetic acid, which has a pKa of 4.8, and we put it in a solution that's buffered at a pH of 4.8, what will be the ratio of conjugate base to conjugate acid? Well, we've just defined that. If the pH is equal to the pKa, then A minus will equal HA. In fact, you can see this in the Ka definition. If A minus equals HA, then A minus divided by HA is 1, and Ka equals H plus. Or, if Ka equals H plus, pKa equals pH. So you can see just from the equilibrium constant, the definition, pKa is equal to the pH at which an acid is half protonated. Now let's look again at acetic acid, and let's say that there's some of it in your blood. Can you tell me how you might get acetic acid in your blood or in your body to begin with? What might acetic acid be hydrolyzed off of? How about an acetyl group? For example, acetylcholine can be broken down to make acetic acid. So we have acetic acid in your blood. What will be the ratio of conjugate base to conjugate acid? Try to make an estimate. My first question is, if the pH were 4.8, what would be the ratio? 1 to 1, right? Now, the pH of blood is what? It's 7.4. So that's a higher pH. So will the ratio be greater than 1 to 1 for base to acid, or will it be less than 1 to 1 for base to acid? In other words, is there more base or more acid? Well, again, at 4.8, they're perfectly balanced. We've gone up 3 pH units. That means there's much higher pH, much fewer protons. If there's fewer protons, that means that you're going to be more in the conjugate base form. So think a lot about this, because this one simple rule you're going to apply to absolutely every problem you do with pH. At 4.8, we know they're 1 to 1. What do you think the difference would be if it's 5.8? Again, it's more basic, there's fewer protons, so you're going to have more of the base form. And it turns out these are logarithmic scales. So instead of 1 to 1, it's 10 to 1 base to acid. What do you want to guess it'll be at 6.8? Please guess. Another tenfold, it'll be 100 to 1. And at 7.8, 1,000 to 1. Now, 7.8 is not far from 7.4. And that's the type of thinking I want you to be able to do. I don't want you to go, oh, we better go between these pH logarithmic units. To me, to say it's 1,000 to 1, that's close enough. So, do you see the principle here? Anytime you have a problem where someone gives you the pKa and the pH, you can simply go, okay, we know that if the pKa equals the pH, that the conjugate base and acid are equal. Now we need to say, are we at a higher pH, in which case there's fewer protons, or are we a lower pH where there's a lot more protons, which will stick to the conjugate base and make more of the acid? Now, once you know the direction, then you can see how many pH units, and for each pH unit you move away from the pKa, there will be a tenfold difference in the ratio. Now, that is what I would call the poor man's Henderson-Hasselbalch. And if you do a few problems with this, it's going to make tests a lot easier. You don't have to formally go into Henderson-Hasselbalch. However, there might be problems which are more complicated and don't just involve being given the pKa and the pH, in which case you might need Henderson-Hasselbalch to solve it algebraically on a more complicated problem. So, we've been given these definitions of pKa, Ka, pH, and chemical equilibrium. Can you derive the Henderson-Hasselbalch equation, which says that the pH is equal to the pKa plus the log of A minus over HA? You can try to derive it. It's worth a little bit of a stab. But let me remind you of something again. What happens if A minus equals HA? Then you would have pH equals the pKa plus the log of 1. And what's the log of 1? 0. So the pH equals the pKa. That's such a fundamental and important definition that I want to make sure you remember it. But I'm going to go ahead and derive it, and simply I will remind you that we're looking at an acid dissociation reaction. So all we do is take the definition of an equilibrium constant, the equation that says Ka is equal to products over reactants. Now we want to solve for the pH, so let's solve for the proton concentration first. To get protons alone, we will divide both sides by A minus, multiply both sides by HA, and we get that the protons is equal to the Ka times HA over A minus. If that was too fast, play with it a little, solve for H. There's multiple ways of doing it, and you can do a lot of steps, but we now have the protons alone. The next step, we're trying to find the pH, which is the negative log, so let's take the logarithm of both sides of the equation. The logarithm of the proton concentration is equal to the log of the Ka times HA over A. Now we can multiply both sides by -1. And I'm going to go another step here. And this is a principle of logarithms. Look, you don't have to do this, but you're welcome to come to me, or I can make a video on this. But logarithms are kind of interesting, that the product within a logarithm is equal to the sum of the logs. So that the log of Ka times HA over A minus is equal to the log of Ka plus the log of HA over A minus. So we separated the logs and we multiplied by -1. So the negative log of the H plus is the pH, the negative log of the Ka is the pKa, that fundamental definition. Now, the same rule that says you can separate a product in a log to be the sum of the logs, you can do the same with, it's exactly the same thing with a quotient, that basically the negative log of HA over A minus is equal to the positive log of A minus over HA. Again, these logarithmic rules, you can come and talk with me about them, but the point is that we have the pH is equal to the pKa plus the log of conjugate base over conjugate acid. Now, I want you to do one other thing with the Henderson-Hasselbalch equation. What if conjugate base equals conjugate acid? If pH equals pKa, then you can subtract pH from both sides and you'll get 0 is equal to the log of A minus over HA. How can you get 0 from a logarithm? Only if A minus equals HA, so that 0 equals the log of 1. The definition of a pKa is that it's the pH at which the conjugate base equals the conjugate acid.